Started now.
Okay. Yeah. So what is happening here? This summation of small, this xi, this is equal to 0. So summation of capital I, that is equal to 0. And summation of ki capital xi, that is also equal to 1, as we have used here. That is equal to 1, you see here. This we are writing as 1, this we are writing as 0. So eventually, what we are getting, this alpha hat as alpha plus beta x bar, what we have here, sorry, and then here beta x bar, and then this part. So beta x bar is cancelled out. So eventually we are having alpha hat as alpha plus summation of 1 by n minus x bar into ki whole into ey. And if you take mathematical expectation, you can see here that mathematical expectation of alpha hat is equal to this into mathematical expectation of ui, and by assumption this is equal to 0. So this component is cancelled out. So we are basically getting expectation of alpha hat is equal to alpha. That means mean of alpha hat is equal to alpha. Now what would be variance of beta hat? Variance of alpha hat. Variance of alpha hat is equal to expectation of alpha hat minus expectation of alpha hat whole square. And we have already seen expectation of alpha hat is equal to alpha. So variance of alpha hat is equal to expectation of alpha hat minus alpha whole square. That means what we are doing, basically we are taking this to the other side. That means we now need to get expectation of this whole square. This part. Basically this part. Mathematical expectation of whole square of this, because alpha will go to the other side. Alpha is equal to this. So alpha hat minus alpha would be equal to this. Hence variance of alpha hat is equal to mathematical expectation of alpha hat minus alpha whole square. That means mathematical expectation of this whole square. This is what we have written here. And then, this is the non-stochastic component. So when we are taking mathematical expectation, this will be basically coming out of the expectation part, and then we will have expectation of ui square. And expectation of ui square is nothing but the variance of ui. Right? And the cross product term we are not writing here. That is, say I and j, because we know expectation of ui and uj is equal to 0. So that what we are not writing, just to make it simple. Writing this assumption would be enough. And if you want to understand, you can just go ahead for deriving it in detail. Just take one example, that 1 by n minus x bar into ki into ui summation whole square. Just take two observations, 1 and 2, and see there would be a product term like this. There would be a product term like this, and mathematical expectation of that would be equal to 0. So we are now left with this component. And you know this is equal to sigma square. So eventually we are having variance of alpha hat is equal to sigma square into this, which is equal to sigma square, and then you just make a square of it. And through simplification, you will be getting this. So what we are getting, alpha hat is distributed normally with mean alpha and variance this. So what we are doing, first we are expressing both alpha hat and beta hat as linear function of yi, because yi is normally distributed, hence both alpha hat and beta hat will be normally distributed. Then what we have done, we have derived the mathematical expectation of alpha hat and beta hat and also their variances. So what we are getting? We are getting alpha hat as normally distributed with mean alpha and variance sigma square into 1 by n plus capital X bar square divided by summation of small xi square. And we are getting the mathematical, the distribution of beta hat as normally distributed with mean beta and variance sigma square by summation of small xi square. Now these distributions would be very, very important when we go for discussion on testing of hypothesis.
Excuse me, sir.
Yes.
Sir, in this proof where we are taking out for sigma hat,
Right.
is in this, like, I didn't understand that from expectation of sigma, like from whole square, how we
Yeah,
came to.
this one you are talking about, right?
Yes, sir. From there, how we like came to that. Like I
This
understood
one,
that we are.
right,
Yes,
right,
yes,
right. So basically, this is a summation, right? This is a summation, right?
yes, sir.
Summation, I mean whole square of the summation. Just think of it in this way, 1 by n minus x bar k1 into u1 plus 1 by n minus x bar k2 whole into u2 and then that square. So when you do that, say it is a plus b whole square, right? So you will have a square plus b square plus 2ab. Am I right? Hello?
Yes, sir. So like, but like, I understood the expansion of it, but what will be a and b whole square? Like, we are getting like a lot of terms, right? Acha, we are
But
taking
other
only
terms
two.
should be cancelled out because when you are writing the 2ab part, right? When you are writing the 2ab part, it will be what? 1 by n minus x bar into k1 whole into u1. Then again 1 by n into 1 by n minus x bar k2 whole into u2. Now when you do that, there would be a term u1 u2 and mathematical expectation of that would be equal to 0 by
Okay.
assumption. So what I'll do, I just write this derivation in detail step by step. I think that would be quite useful, isn't it? I
Yes,
mean,
sir.
how I am arriving from here to this point, I'll write all the steps in detail, the way I have done for the other component. Will that be all right?
Yes, sir.
I'll add that. like this Word file, what I have done, the way I have written down it in detail, I will be writing that part also in detail. Both derivation of distribution of alpha hat and beta hat. I
Sir, I
understand.
have
I mean,
one doubt.
all of, sorry.
I have one doubt.
Yeah.
We are getting the distributions of alpha hat and beta hat, and the expectations are alpha and beta. But we
Right.
don't know the values of alpha and beta, right?
Right.
So we are not practically getting the distribution. Like we just know that the distribution is
This
normal,
is
but we
distribution,
can't.
right? Very good question. Very good question. We'll be basically using the estimators. And when I just go for testing of hypothesis, I'll bring in that part. It's a very good question. We are getting, like, we don't know sigma square also, isn't it? Do we know sigma square? We don't know. What is sigma square? What is
Yes,
this
sir,
sigma
we
square?
don't know.
No,
Variance
no.
of
What is this
y.
sigma square actually?
A variance
Variance of
of UI.
Variance of
magnitude.
ui. If you don't know ui, how will you get variance of ui? Isn't it? So we don't know sigma square, we don't know alpha. You are absolutely right. But then we'll be using estimators. I'll be discussing on that. Why we don't know ui? Very simple. Like what someone had asked me, like see this diagram. What is ui? ui is basically deviation of actual observation from the population regression function. And we don't know the population regression function. Hence we don't know ui. If we don't know ui, we also don't know its variance. So not only alpha is not known, sigma square is also unknown.
So, but even if we estimate the value of alpha, then also it won't be the same. So we won't get the exact distribution of alpha hat.
That is why.
Hello?
Yeah. Hello. Is someone else saying something? Is someone saying something? Anyway, so what basically I am saying here, that yes, we don't know alpha, we are basically getting an estimate, and that estimate we are getting from the sample. But remember, in the method of OLS, we are going to estimate this alpha in such a way that the sum of the square of the u hat I, that is minimum. That is minimum, right? So we are basically trying to minimize the deviation or the errors that we are having in the process. This is point number one. Point number two, in case of testing of hypothesis also, whatever we conclude, we'll be discussing this testing of hypothesis part. You will see whatever we conclude based on these estimates, these conclusions are also having some errors. So the conclusions in statistical tests, they have some errors. Like you might have studied type 1 error and type 2 error. Have you studied that? Type 1 error and type 2 error? Hello? Hello?
Yes,
Yes, sir.
sir.
Right. So this type 1 error, type 2 error, if you see the distribution, what do? We say, that's what I was discussing at the beginning of this course. When we go for testing the hypothesis beta is equal to 0 or alpha is equal to 0, we basically prefer to have 1% significance level as compared to 5% significance level. Why? Because in testing of hypothesis, these type 1 error and type 2 errors are attached. That's my point. You are right that we don't know alpha, we don't know beta, we don't know sigma square. We are estimating them from the sample, and then subsequently we are carrying out the hypothesis testing. But when we go for testing of hypothesis, the conclusions are based on certain errors. There are some errors embedded in testing of hypothesis.
Sir,
And second,
hello.
yes, alpha hat is not exactly equal to alpha, or beta hat is not exactly equal to beta, but I will prove later on mathematically that these alpha hat and beta hat, the OLS estimators of alpha and beta, will satisfy their desirable properties. That means what? Alpha hat may not be exactly equal to alpha, but it will approach to alpha when n tends to infinity. Remember what I said. Here we will be focusing on three desirable properties. That alpha hat will be unbiased, so is beta hat. They will be efficient, and also they will be consistent. So even if alpha hat is not exactly equal to alpha, if it is consistent, then it will be asymptotically equal to alpha. Similarly, mathematical expectation of alpha hat is equal to alpha if alpha hat is an unbiased estimator of alpha. That is why ensuring that these estimators satisfy the desirable properties, that is extremely important. And they will be satisfying their desirable properties provided the assumptions are satisfied. And that is why in the initial discussions, I told repeatedly that a large component of this course is for discussion on these assumptions and testing for their validity, and if there is any deviation, then application of remedial measures to ensure that these assumptions are valid. So you raised a very important question. I'm just summing it up in my answer. I would like to see it from two perspectives. One is that when we are estimating alpha hat and beta hat, these two estimators, if they satisfy the desirable properties, then three things will happen. One is mathematical expectation of alpha hat would be equal to alpha. That means even if a particular alpha hat is not equal to alpha, their average is equal to alpha. Second, if it is consistent, then as n tends to infinity, alpha hat will tend to alpha. And third, if it is efficient, that means if it has minimum variance amongst all the unbiased estimators of alpha, then obviously the deviation is minimized and this alpha hat would be closer to alpha. So this is basically from estimation point of view. By definition, or we'll prove it subsequently, that these OLS estimators actually satisfy all these desirable properties provided the assumptions are valid. The assumptions hold. So what we'll do? After estimation, we'll test if the assumptions are holding. If the assumptions are holding, then these estimators will be unbiased, efficient, and consistent. If they are not holding, we'll apply some remedial measures to ensure that they hold. So this is one approach from estimation point of view. Then we go for testing of hypothesis. And again, the testing of hypothesis, these statistical tests, they have type 1 error and type 2 error. And there what we do? We prefer 1% significance level to what? 5% significance level to 10% significance level when we are testing the hypothesis that beta is equal to 0 or alpha is equal to 0. What are we doing there essentially? By switching over from 5% significance level to 1% significance level, we are actually widening the confidence interval. We are actually raising the chance that beta is equal to 0, means the null hypothesis is not rejected. Again, for some of you, it may not be exactly clear at this stage. I'll discuss in detail on this testing of hypothesis. You will see that as we switch over from 5% to 1% significance level, the confidence interval actually widens. And then the chance of non-rejection of the null hypothesis also goes up. Despite that, if we can reject the null, then we can say that beta is different from 0 in a robust way. Again, this part, this testing of hypothesis part may not be exactly clear at this stage. I'll be discussing this on in detail. So I would like to answer your questions from these two angles, but again, in subsequent discussions, I think your question, but it's a very important question, and I
No,
hope in
sir, I
subsequent
understand
discussions
what
you
you
will
told.
get a clear idea. Yeah, please.
I understood what you told.
But it's a very important question.
Yes, sir.
In the same way, the other question was that why are we going for PRF, or why are we discussing about PRF if it doesn't exist? Okay, I think it's going to be 1 o'clock. Just we'll continue with this discussion in tomorrow's class, and I'll add the detailed derivations for all these. Some steps I skipped, uh, maybe at this stage, that is causing some